Entonces, esta próxima charla, we are super excited about this one. When we were debating which speakers we wanted to invite, this is definitely one that stood out. Not only because the CFP was super creative, but we were also really excited. It's like, I asked Lucas, is this math heavy? He said no. He said it's function heavy, which sounds even scary. But we are super confident that this is going to be like a very thoroughly thought out, explained talk. Lucas da Costa comes all the way from Brazil through London, where he's where he's currently working at Converge. An interesting thing that... Oye, chicos, en serio, por favor. Que es muy difícil hablar cuando todos están hablando sobre mí. An interesting thing that Lucas said was that he agrees Colombian coffee is better than Brazilian coffee. Ooh. Anyway, without further ado, let's give a big, big round of applause to Lucas da Costa.
So, well, hello everyone. So I know that the title of my talk is a bit cryptic. And yes, I do talk about birds, but this is essentially a talk about Lambda Calculus, which is what is behind functional programming. So just like three machines gave birth to the object-oriented paradigm, Lambda Calculus gave birth to the functional paradigm. And well, in this talk, you don't need to trust me about why learning Lambda Calculus is important because, well, you trust Stack Overflow way more than me. So if you ask Stack Overflow how helpful it is to know Lambda Calculus, and then you do what us programmers do best, which is look at the first accepted answer, and read the first phrase, you see that if you want to program in any functional programming language, it is essential. So I want to highlight this word, essential. Well, so this is the actual only slide that has Lambda Calculus itself on it. So Lambda Calculus consists of just 4 tokens, nothing else. So we have identifiers, abstractions, which are function definitions, and it's important to notice that these abstractions can only take one argument. Function application, which we'll treat as invocation here, and grouping, which is when we use parentheses to disambiguate stuff, right? So, you know, I could be showing you a bunch of things about monads, comonads, functors, all of that, but instead of just showing a bunch of concepts, I want to play a game. And, well, this is a game because I can lose. I'll be doing live coding all the time. I want to rewrite JavaScript without booleans, numbers, objects, string, classes, without any of that. Yes, exactly that. We rewrite JavaScript with nothing but functions. And this is nothing but Lambda Calculus because all functions can only take one argument. Functions can return other functions. And we, of course, can use parentheses, right? So here, the important thing to notice is that if I want to use 2 arguments, I need to have curried functions, which are functions that return other functions. So I can have a function which takes E, then takes B, and inside the second function, I can use those 2, right? Because they're in scope. So let's get started winning JavaScript and opening the terminal. So when I'm done with this, you see that I can replace this whole function only with function. No functions, no numbers, no pluses, no multiplication, nothing of that. And function starts with fun. So I think this is going to be nice. Well, the first thing I'm going to replace here is booleans. So if you actually think about what a boolean really is, a boolean just helps us deciding between 2 things, right? In this case, we can decide between yes or no in this ternary. So if I have true, I can console log my result. And it's going to be yes. If this was false, it was going to be no. You can see the results here on your right, okay? So how can I replace booleans with functions? Well, if I want to have true, well, I can make true a function which takes A, returns a function which takes B, and returns the first thing, right? Because this is what this ternary is doing. It's taking 2 things, yes and no, and returning the first one. If I want to have false, I can replace this by false and make it return the second thing I pass in. So now I can replace my true with this function, right? And it will give me the exact same result. Yes. If I have false here, I get no. And I can even have some syntax sugar and use if, which is just the identity function. So I just get my Boolean and return itself, right? So it doesn't make any difference if I wrap this inside an if. Cool. So we have just replaced the Booleans. Now we need to replace numbers. Well, replacing numbers is a bit tricky because we need to ask ourselves, what is a number anyway? Well, is this a number? Well, the answer is like yes and no, because this is a number, but this is also just one of the ways we have to represent you, right? We can represent you in binary, in hexadecimal, Romans, like many ways that we have of representing you. But what numbers actually mean is repetition, right? So this is two oranges, two glasses, and we need to dissociate representation from meaning. Well, if you just have functions, and you want to represent repetition, you might as well just repeat your functions, right? So if I want to have number 1, I can have a function which takes f, returns a function which takes x, and applies x to f. If I want to have 2 and 3, I can just repeat this function application, and then this means repetition. And this might sound weird. I know it sounds weird. I know you're looking at me like, oh, what's this guy doing? So let me make it a bit more visible here. So I can have a show function which console logs something, right? So if I want to repeat show twice, I can just do 2, show, and then if I do show twice, and if, oh, I can hear my voice, that's nice. Now if I do show twice, sorry for this console log, I get 2 somethings. And I could say that my way of representing numbers is just by the number of times I repeat something. You know, that's one valid way of representing a number. But here I'm going to do a bit of a cheat. So I'm going to have a toNum function, which will convert our number functions to the decimal representation we used to. And this is just so that we can see the results. We don't need this. So this function has a counter, which starts at 0. And since all our number function does is repeat whatever's passed to it, I'm going to pass it a function which increments my counter. So if I pass it 3, oh, I missed that f here. So if I pass it 3, it's going to invoke this function which increments the counter 3 times. So I'll have 3. So I can now console log I, and if I do toNum 3, I get 3. Okay, so now we can see numbers. But also, if I want to have 0, I can just never apply f. And I can think of this as once, twice, and thrice, because they just repeat things, right? So calling the functions this way might be a bit more easy to understand. Okay, so now we have replaced numbers. We might as well just replace arithmetics. And I'm going to start replacing arithmetics by replacing sum. So what is a sum? Well, great question, isn't it? So when you do 4 plus 2, all you're doing is getting the successor of 4 twice, right? So you're first getting 5, then 6. So I can say that sum is going to take A, B, and then I'm going to repeat the successor function A times for B, right? So if I have 2 and 4, I'll be getting the successor once, 5, and then 6, and that's my sum. But I don't have the successor function. So I need to implement this. And it's so interesting to see like how you can compose those functions to build more operations and build more stuff on top of that. So here, for my successor function, well, to start, I'm just going to take n and return n. So let's do toNum successor of 3, right? So if I do this, I should get back 3, right? As you can see here on your right, I get back 3. Because I'm just returning whatever's passed here. If I want to always return 1, I can copy the definition of 1, and I can, paste it here. And now, whenever I invoke this function, I'll return the function which represents 1. Okay, so if I do successor of 3, I get back 1. Whenever I want to increment this number, I just need to wrap it inside another function call. So I start getting 2. Now, inside here, if I still want to return the same number, I can just do n times f and apply x, right? Because n repeats a function, and the function I want to repeat is being passed in here. So this will always return the same number. And how do I increment numbers? Well, wrap it into a function. So now I have the successor function. Okay, now you're getting 4 for the successor of 3. And I can define now 4 as the successor of 3. And I can even define 5 as the sum of 2 and 3. And I can now console log both with 4 and 5. And there we go, 4 and 5. Simply works. Thank you. Okay, I'm glad I have made no mistakes so far. If I want to do multiplication, well, I just need to take a and b. And now I will take the function I want to repeat. Right? So if I repeat this function b times, I'll get the very same number b represents. But now, if I repeat it a times, I'll be doing multiplication. So now I can define 6 here as the multiplication of 2 and 3. Right? So if I log 6, I'll hopefully get the right result. Yes, I did. And now I can define exponentiation. So since these functions, they just repeat each other, let's say I have 2, 2, 3, right? So this means I'm just repeating the twice function 3 times. So I'm doing twice, twice, twice. And what is this? Well, this is just this, right? I'm just multiplying the function that does repetition, which is a, by b. So now I can define 8 as exponentiation 2 and 3. And if I log 8, I get 8. Cool. So now things start getting a bit hard, as if they weren't hard enough already, right? So for subtraction, I can follow the exact same path as I've done for addition. So for subtraction, I can define it as taking a, b, and then I'm going to repeat the predecessor function, b times, for a, just like addition, right? Just like a sum. However, for me to explain this, I need to explain wrappers, pairs, the predecessor function, and only then I can get to minus. But this is going to be a smooth ride, I promise you, like, it's going to be nice. So now, let's implement a wrapper, right? So a wrapper will just take something, anything. We'll take a function, and then we'll apply a to that function, right? So let me just comment this line and remove this, so we don't get anything on the console. Okay, so my wrapper, we can think of it like a box, right? So when we pass a, it's as if we're putting a in a box, which can be opened with a function, right? So I can have here a box. So this box has Colombia inside, for example, right? So when I do this, I'll get back this function. And in here, a is Colombia, right? So now I can show you what's inside the box. I can open the box by passing console log to it. And I get Colombia. And pairs are nothing but boxes with 2 things inside. So for a pair, I can have a and b inside my box, and apply both here. Okay, so now let's make a pair with Colombia and Brazil, right? And, well, what do I do if I want to retrieve one of them? I already have functions which select either the first or the second thing, right? When I pass 2 things to them. They're true and false, right? So here, I can also call these functions first and second. Because here, when I apply a and b to this function, I'm always going to return a for first and b for second. Which means that I can get the first item inside my box and the second item of my box by passing the function I want here. So if I console log this, oops, I missed a parenthesis. This is looking like Lisp. Now I get Colombia and Brazil. I heard that. Okay. Cool. So now that we have pairs, okay, I think now it's going to get a bit more complicated. Don't worry. It's going to be fine. We're going to go step by step. The increment pairs function, which is necessary for us to define a predecessor. Okay, so we have a pair, right? We have a box with 2 things inside. So we can have a box with 0, 0. And when I increment it, I'm going to copy whatever's in the second place to the first place, and increment what's in the second place. Sounds complicated, but 0, 1 just becomes, 0, 0 just becomes 0, 1. 1, 2 becomes 2, 3. 4 and 5 becomes, anyone? Anyone? Exactly, 5, 6. See, easy, easy, right? So now, if we repeat the increment pairs function twice over 0, 0, I get 0, 1, 1, 2, 2, 3. And if you notice that the first item in this pair is 1 less than the number of times I repeated this operation, you see that this is the predecessor function. So if I repeat this operation 3 times, the first item in the pair is 2, which is the predecessor of 3. So now I can go on and implement that. And this is the part I've made more mistakes when I was live coding during practice. So here, we're going to have first my increment pairs function, right? So I take a pair P, and I'm going to get the first item inside of P. Now I'm going to put that into another pair. Oh, I think this is the second, sorry. Okay, so I'm going to put the second item of my pair inside another pair. And now I'm going to get the second item again, and I'm going to sum 1 to that. Can you still see this? Okay, cool. So if I made the parentheses right, I'll get the right result, and I'll run this for 0, 0, which is just a pair with 0, 0. Hopefully, I didn't miss any parentheses. So now, let me run increment pair, whoa, dangerous, over 0, 0 once, and get the first item. And hopefully, whoa, nice. So now I just need to do tunum. I get 0. I get the second one, 0, 1. Okay, so it's working. If I repeat increment pair twice, right? So I need a parenthesis here. I get 1 and 2. Okay, great. Now I just need to implement the predecessor function. So the predecessor function consists of taking a number, repeating the increment pair functions by that number for 0, 0, and then getting the first item of the pair. So now I can define 7 as the predecessor of 8. And if I do tunum, 7, 7. Magic. Okay. Okay, I hope you're liking it. So now that I've done this, so I was supposed to actually go through this, but I think you got it, so I can skip it, which is good. No, but this is what I've just done, right? This is just slides for what I've just done. See, you understood it. You don't need the slides. Even better. And I save time. Okay, so now I can replace Boolean operators. So I can replace things like not, right? So if I have here not, well, what is a Boolean? Well, a Boolean takes two things and returns either the first if it's true or the second if it's false. So not will take a Boolean. We'll take those two things, right, A and B. And then if I did this, I would just be repeating the Boolean, right? But if I want to invert the Boolean, I just invert what I pass in. And all of a sudden I have not. So I have just replaced not with functions. And I can go even further and replace things like and. So what is and? Well, and will return true if we have true and true, right? So let's take a Boolean A Boolean B. And now, if A is true, it means I also need to check B, right? Because both need to be true. So if I return B, if B is true, this function returns true. Otherwise, it returns false, right? However, if A is false, it needs to return the second thing. And if A is false, I can just return A, because I'll be returning false anyway. And this is and. And I can show you this by logging a Boolean here. So I'm going to do and, true, true, yes, and no. So you're going to select between yes and no using this, right? So here I have yes because both are true. If I change one of them to false, I start getting no. So I've just done and, right? And now, to make it even more fun, I can have less or equal than, I can have equals, and I can have greater than. Okay? So for me to compare two numbers, I have to have a point of reference, which in this case is going to be 0. So whenever I subtract two numbers, I cannot have anything that's smaller than 0, because a 0 already means that I'm not applying the function any times, right? So if I try to subtract 3 from 2, I'll get 0. I'll not get minus 1, okay? So now, if I go and try to implement is 0, so that I can use it on less or equals than, you see something very impressive, right? Because like, if you notice in our, like, in the programming languages used daily, you see that false and zero, like, can be used interchangeably, right? So both are falsy. And false is the same thing as zero. Isn't it amazing? Like, false takes A and B and returns B. And zero takes two things and also returns the second one. So they're the exact same thing, false and zero. So things just build themselves. It's beautiful. So if I have E0, I can take a number A, right? So if A is 0, it's going to return whatever is here in the second place. So that's true, right? So if A is 0, returns true. Otherwise, it needs to return a function which always returns false. And that's true false. That creates a constant which always returns false. Okay? So now I can even test this by using it on less or equal than. So I take A and B. And now if I subtract A and B, if the result of that is 0, then it means that A is either equal or smaller than B, because that resulted in 0. For equals, I can check if the subtraction of A, actually, I'm going to cheat here. Should I? Well, I think I'm going to take A and B. And then, if both A is less or equal to B, I'm not going to cheat. Okay, I'm not going to cheat. So if A is smaller or equal to B, and B is smaller or equal to A, well, it means they're equal, right? Because if both these conditions are true, it can only be equal. Okay? So now, greater than just defines itself. Because greater than is anything that's not less or equal than. Right? So now I can test this by doing greater than 3. And hopefully this will work. 22. Oh, sub is not defined. Whoa. Sub, that's because I didn't define subtraction. Oh, I'm sorry. Okay, so I know what's wrong and I can fix it. Because subtraction just takes A and B and repeats the predecessor function B times for A. Okay, now it's working. Okay, I should have brought an Apple Watch to see my heart rate. Okay, so 3 is greater than 2. This is yes. This will hopefully return no. Yes, okay, it's working. So now I'm pretty confident this works. So now in this function right here, I have 9, 1, and 12. This is a simple function. If A is equal to B, it multiplies A by 2, sums B. If A is greater than B, we do A minus B. Otherwise, we do A times B. Right? So if I do this, 9, 1, and 12, and now I have this function using only functions. Okay. Okay. And I can do this because Lambda Calculus is string complete. So you can write any program that was ever written or that will ever be written using only Lambda Calculus. And what I've done here is not really JavaScript. So I'm just translating JavaScript, Lambda Calculus to JavaScript. Right? And now that I've ruined JavaScript enough, I'll go even further and I'll ruin JavaScript with birds. So what are birds? Well, birds are just combinators. So combinators are functions that don't have any free variables. So a free variable is a variable that's not bound to an argument. As you can see in the first example there, with context, B comes from another place, comes from, I don't know, the universe. Okay? And in the second one, both A and B are bound to arguments. So this is a combinator. The second example is a combinator. And well, why do we call them birds? Because of this book by a guy called Raymond Mullian, in which he explains combinatory logic by giving you a bunch of puzzles, and then you need to solve those puzzles by using the birds he gives you. And these birds are nothing but combinators. So he names combinators after birds. And combinators are what we've just done, because all of our functions just have bound variables. So the idiot bird is just our if, the identity function. The kestrel is just our true. It takes two things, returns the first one. The kite takes two things and returns the second one. So it's just false. So all of these birds, all of these combinators, they're things we have already done. The cardinal is not, inverts the order in which we apply things to a function. Pairing is the Vireo, so it's a box with two things inside. The bluebird, which is the very title of this talk, which is a reference to Bukowski, Spo, and Bluebird, is the very essence of functional programming, which is function composition, right? So the bluebird here, it takes a function f, function g, and a, and then applies g of a to f. So this is nothing but multiplication, right? This is why it's so beautiful. Like, things just build themselves. The thrush, well, the thrush is just Orapa. The starling, well, the starling is a bit, it's a bit, I don't know. Like, so, okay, we take f and g and x, and then we apply g of x to f of x, right? And then we can start replacing our functions with birds, because the successor function can be replaced by the starling of the bluebird, right? And I don't have time to go into this, but I can show you this later. And if I have addition, I can start replacing it by birds, and addition becomes this. So now, you can go all over your code base and start replacing it with birds. I'm sure you're going to make lots of friends in the office, and everyone's going to love it. You know, like, oh, have you seen that bluebird over there? Whoa, that's nice, amazing. And now I can even bring the birds. Well, I can even show you the birds working, because I have birds here. So I'm going to put a bunch of birds in my code base, right? And now I can replace successor and sum with these, right? So let's go to successor and sum and delete them, right? So these definitions of successor and sum just use birds. And if I save them, I still get the same result. So, well, I have ruined things enough, but I want to ruin things even further, and I'm going to ruin the birds. Because you only need 2 of them. We don't need any other birds, right? We only need S and K. So this is the smallest possible combinator base you can use for having tree incompleteness. Some people call this also SKR calculus, just because, you know, it's more convenient to have I. Oh, because this is already very convenient, right? And, well, but in fact, you can derive I by combining S and K. So Ki becomes this, which is just Ki. Whoa, beautiful, isn't it? Bluebird is this beautiful thing. And, you know, I can go here, and I have these birds. So I can just copy and paste them. Oh, I didn't copy everything. So I can just copy this and put it here. And now, if I do this, oh, I replaced these functions, which I shouldn't have. Sorry. Let me copy this again. So if I replace my birds with these birds, so as you can see, the ibis and the kite and the bluebird, you just use other birds. So if I save this, I still get the same result. And I could, in fact, replace everything with S and K, right? And pairing, well, pairing is really easy, really, really easy. You know, I mean, I do this like all the time, you know, like when I'm in my company, I'm like, okay, S, K, K, S. Everyone loves it. Well, and what does this mean? Well, it means that we can replace all functions, all code by functions, and we can replace all functions by combinators, and all combinators by S and K. We can then replace all code by S and K. And there's some places that do it for you. I mean, don't do this in production. Do I need to have this warning here? Well, now I think I need to apologize, because now you'll be really interested in all those things, including maths, trademark, computability theory, functional programming, combinatorial logic, compiler theory, and even wanting to frame ghetto pictures to hang in your room, and, you know, reading a bunch of papers which you don't understand, and then, you know, like, yeah, it's just like, it's really hard. So, well, thank you very much for being here today. Thank you. Well, thank you so much. You can follow me on Twitter. On my website, there's a bunch of other posts about Lambda Calculus. In my website, I even explain the Y Combinator, which is probably the most interesting thing we have in computer science. And this is the reason why Y Combinator has the name it has. And here's a bunch of other references. So I highly recommend this first talk by Tom Stewart, in which he does what I've done in the first part of this talk. So he basically replaces Ruby code with functions, right? And all of these resources, they're really amazing, especially these classes about Lambda Calculus from the Arizona State University. I hope you have liked it. Thank you very much.